Hello,
We're
space
live.
fans! Welcome to another awesome conversation we're having here with our, I guess, becoming resident now. I don't
Mhm.
want to oversell it too much, but uh, our astrophysicist, Astro Katie, Katie Mack.
Hello.
How you doing, Katie?
Good. How are you doing?
I'm doing well. I've actually had quite a good night so far, and been
Good.
hanging out with a lot of space fan and nerd friends over here in LA. I
You've
know.
been playing. You've been playing Cards Against Mars. I am really jealous.
I have. So Cards Against Mars is a play off of Cards Against Humanity, but with uh, JPL friends that work with robots on Mars. So we've been having a lot of twisted good times, and we got to see both the International Space Station and the Hubble Space Telescope fly overhead all in one nerdy evening. So it's
Pretty
been
cool.
awesome. It's been really cool.
Yeah.
So our topic of conversation for this session is on gamma ray bursts. They've been recently in the news,
Yes.
and kind of just not really dispel myths, but kind of go into what caused us to think there was a gamma ray burst, what and finding out that it wasn't, and then digging into the science of it. So, before we go further with that, let everyone know how you can be in touch with us. So the easiest way is either use the Q&A app, which you can find on both YouTube and Google+. It should be down on the little bottom right here, or over there, depending on my mirrored image. Um, and then type in a question. That way I can timestamp it and answer it when that goes on. Or leave us a question on YouTube or on the Google Plus event. I'll be checking those out. And we're also on Twitter. So I am at Scientific Scott right here, and Katie is
I'm.
at
I'm at Astro Katie, which is over there somewhere.
Astro Katie. Woohoo!
Yeah.
All right.
Yeah.
So what's been up with gamma ray bursts? There was a big news thing that came out
Yes.
the 28th of May, I want to say it was, that there's a gamma
Yeah.
ray burst or something, going
Yeah.
on. What does that mean, and why was everyone so excited about it?
Okay. So we got really excited. Somebody. So there's a telescope called Swift, which is a gamma ray burst, a gamma ray telescope. It has an X-ray detector and it has gamma ray instruments. And Swift is designed to see gamma ray bursts. Okay, so it's called Swift because it's fast. Basically, it has a detector
Ah, I see
that
what they're
that
doing.
yeah. So it's not actually an acronym. It's one of these very few instruments that's just given a name. All right. So it's a satellite, and what Swift does is it detects bright bursts of radiation, and then when it sees something, it quickly looks at it and tries to take as much data as possible. And it's detected a lot of gamma ray bursts. And so when it detects something, when it sees something that looks like it might be a gamma ray burst, it automatically triggers an alarm, and people get like text messages. Like the people
That's
who
awesome.
work with that instrument, they get like alerts that say there's been a gamma ray burst. And when that happens, um, a memo circulates through the community, and anybody who has a telescope, like who's working on a big telescope, like a professional telescope, or even just people who have like a nice sort of amateur telescope set up in their backyard, um, if it's a bright enough thing, will like go and try and take data. And
Right.
so there's
So here's actually the memo that went out at that time.
okay, yeah, yeah. So whenever there's a some kind of announcement, um, basically anybody who works on gamma ray bursts gets like first dibs on the telescope time to try to observe this, because gamma ray bursts are quick events, and you want to see the afterglow and learn something about whatever caused the gamma ray burst, whatever happened at that spot, whatever's still there.
Hmm.
Um, and so you have to get the word out fast, and you have to try and get the telescope time really quickly, and observe as much as possible. Um, and so what happened was this memo went out, and people who were in the know, who either got the text message or saw the circular, went on Twitter and said, "There's this gamma ray burst." And the exciting thing was that it seemed to be in the Andromeda Galaxy, also
Right.
known as M31, which is right next door. It's
And it's
actually
headed right
plunging toward
for
us.
us.
Yeah, it's gonna collide with the Milky Way in a few billion years. But anyway, so Andromeda's really nearby, and so they tweeted, that there's this burst that's really nearby, and that's exciting because if the burst is really nearby, then we learn a lot about gamma ray bursts, and we don't want one extremely nearby because
Right.
these are extremely energetic events, and if it were within, I don't know, 100 light years or something, we'd be in trouble. But M31 is not that close, and so it would have been just conveniently close to see something. So this announcement went out on Twitter, and everybody started getting really excited and tweeting about it, and like asking for people to get on their telescopes and try and see something. And there was a hashtag GRB M31,
Right.
and people were sort of writing stuff about it, and IO9 wrote a big long post about it, about what gamma ray bursts are and why this particular one is exciting. And then, as the day went on, it became clear that the burst looked a little bit odd in terms of the triggering and the data that they got from it. And then a number of things kind of went wrong in a way that made it look more like a gamma ray burst than it actually was. And so it eventually came out that it wasn't really a gamma ray burst.
So here's what they saw
Right.
right there.
Yeah, so what they saw was like an X-ray signal basically in the Swift telescope, and it triggered the event thing because it was probably some kind of glitch in the software, and there was an X-ray source in that direction, but it was not a burst. It was actually a constant source that was already known, but because there was a glitch in the software and it was pointing at a source that was bright in X-ray, the telescope got confused. And then there was like a power outage across the east coast of the U.S. that was like right at the wrong time.
All sorts of things happened at the same time.
Yeah. So that made it hard to get the data, and then like people couldn't access the website, and then so it took a few hours, several hours, before it became actually clear that this thing wasn't a gamma ray burst. And the person who really cleared that up is a guy who goes by Swift_Phil on Twitter. I can't remember his full name, Phil something. Phil Evans, yeah.
Okay.
He wrote a nice post explaining that it wasn't actually a gamma ray burst and what happened, what went wrong. So it was kind of a letdown, and there were already like news articles having been written about this, people wanting to get on this right away because it's this big exciting event. And then it turned out not to be true. But it was kind of. But the thing about this, some people were obviously kind of embarrassed about it. But it's actually like because these things are so quick and you need to get the data so fast, you just have to put out the word right away, and you have to get everybody looking at these things with telescopes.
Right.
Because if it is there, you're not going to get another chance.
What I think this really did is it gave a lot of insight into how the science works. Is that it's something we notice. We have an awesome telescope up there that sends out text messages. So you're getting your Twitter update. Amazon shipped your package. Awesome. You're getting this notification. So then people are spreading the word, as many people as possible, to look at that thing, and they're getting excited because this is what they do, this is what they love, and sometimes it's not going to be what it looked to be in the first place, and that happens.
Yeah.
You have to say, all right, well, it wasn't that in the first place, and we actually have. I think our next show will be on something like that, at least with the Bicep 2 data, and we'll dig into that a little bit later too. But so what exactly is a gamma ray burst? Why was everyone excited that it would be that? What does that mean besides gamma rays being on the very, 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 very short wavelength and high energy levels of the electromagnetic spectrum?
Yeah, so gamma ray bursts are some of the most extreme events in the universe. So they are they're something that produces gamma rays, and they're extremely energetic, extremely bright, and they're generally pretty quick. So there are two types of gamma ray bursts that we know about. There's like sort of a distribution of different kinds of gamma ray bursts, and the distinction between the two types is the long bursts and the short bursts, and the division is about timing. So short bursts are like less than 2 seconds. They're really, really fast.
Right.
And the long bursts are up to minutes or something like that. Yeah. So there's this two separate populations of different kinds of gamma ray bursts, and we think that those come from different processes. So the long duration gamma ray bursts we think come from a kind of supernova, like an incredibly energetic type of supernova, also known as hypernova. And so this is the explosion of a very massive star. Mm-hmm. And we think that it's an explosion that happens where the star explodes and becomes a black hole. And that event is so powerful that it puts out this huge amount of radiation, and we can see them from very, very long distances. So these gamma ray bursts can be extremely far away. We've seen them out to billions of light years away. So they're really distant. They can be really distant objects. They're really bright objects. And so long gamma ray bursts we think are associated with supernovae. The short gamma ray bursts are a little bit more controversial. It's a little bit less clear what those are.
Okay, but, like controversy. Tell me more.
Well, no, I mean not. I mean it's only recently that we've had like a really accepted model of what short gamma ray bursts are. We think that they are the merging of two neutron stars. So you have two neutron stars, and they're in a binary orbit, and they come together and they collide. And when they collide, they make this gamma ray burst.
So to find out more about neutron stars, look at our previous episodes where we're talking about supernova remnants and what happens there with that.
Yeah. So a neutron star, if you didn't see the previous episode, is it's like the corpse of a star that's gone supernova.
But it's a zombie because it's still doing things. Which is awesome.
So it's a massive star that collapses, the core of it collapses, and the rest of it gets blown off in a supernova, and the core is made of basically neutrons. And it's this extremely compact object, and it's got often a strong magnetic field, and sometimes it's a pulsar, and it does cool things with radiation. But anyway, if you have two of these in orbit around each other, they can collide and make this incredibly energetic burst of energy that's really, really quick. So these are, less than a couple of seconds, like really quick bursts. And those are harder to study because they don't have so long an afterglow. So supernovae, when they go off, there's a bright burst of radiation, and then there's usually an afterglow with various kinds of wavelengths coming out of that. And so long gamma ray bursts have an afterglow that you can study and learn something about what the object was before it went boom. But with short gamma ray bursts, that's a lot harder to study because they tend to go quickly.
So they just go boom, loud, just short, as opposed to almost like just a little drawn out boom, where we can still get our time to point our telescopes there and really learn it. When it's a shorter one, it seems like there's just not enough time for us to get everything pointed there to really study it quick enough.
I mean, that's why it's been hard to figure out what short ones are, because there's less, unless you see it happen, it's harder to study the aftermath. But with with anything that's a supernova, you blow out a huge amount of material, right? From the whole atmosphere of the star gets blown out, and that atmosphere, as it's expanding, it's radiating radio waves, and it's you get X-rays, and you get all this kind of cooling down radiation as it's coming as it's expanding and coming out. So we think there are two different kinds of gamma ray bursts, and they're from different kinds of explosions. And it's really interesting how gamma ray bursts were discovered, because so they were discovered, I think, in the 60s or 70s, and they were discovered by accident, as a lot of things in
Right.
astronomy are.
Right. So
Um,
tell me, there's no pigeon poop involved with this one, right?
no,
Okay.
no. There's spy satellites and nuclear testing involved.
Ooh.
So what happened was the U.S. government and other governments around the world were really concerned about nuclear testing because it was the Cold War, and people were threatening to blow each other up with nuclear
Right.
bombs,
Right.
and so there were satellites up, orbiting the Earth, looking for signs of the radiation that comes from nuclear test explosions, and so there were satellites up there that were designed to detect the gamma radiation from nuclear testing. And at some point, some of these satellites were up, and they saw these bright bursts of radiation coming not from the Earth but from space. Um, and luckily, they were able to figure out that they weren't coming from the Earth, so they didn't
Yeah.
accidentally start a nuclear war.
Right. I'm glad no one had an itchy trigger finger on the big red
Yeah,
button.
because it would
Well,
have looked pretty bad, right?
right.
So there was something happening in space that was creating all this gamma radiation, and they didn't know what it was. And so over time, they put up more satellites and tried to study these things explicitly, specifically. And so by the mid-90s, we had detected a lot of these bursts, maybe a few hundred or something like that. But we still didn't know what they were. We had no idea what was causing this burst of radiation. And there were lots of discussions about what they could have been. And one of the big controversies around the mid-90s when we were first talking about this was how far away they were. Because these were so bright that a lot of people thought they had to be nearby, because nothing is that energetic in the universe. They're much more energetic than supernova, like typical supernova. These are like 5 or 6 orders of magnitude brighter,
Right.
maybe 8 orders of magnitude brighter than supernova. So really, really bright, lot of radiation in a very short time, and and it seemed impossible that they could be far away because then they would have to be much brighter than we thought was possible. And so one of the coolest things about gamma-ray bursts was how we determined how far away they were. And so basically, there were a lot of people discussing about the sort of main person in this discussion who kind of laid out the argument in a really convincing way is this guy called Boda Baczynski, who was a professor at Princeton University when I started as a grad student there, and really, really sweet guy. Unfortunately passed away during my time at Princeton, but I got to know him a little bit while he was there. And he was like sort of the first person to lay out this really, really convincing argument for how far away gamma-ray bursts were. He wrote this excellent paper called "How Far Away Are Gamma-Ray Bursters?" They were called bursters, not bursts at the time.
Right.
And let me just read you like the first 2 sentences of this
Yeah.
paper, because it's really cool. So he says, the title of this debate is "The Distance Scale to Gamma-Ray Bursts. However, the real issue is, how do we do science, how do we reason, and what reasoning do we find convincing?" So what he did is he laid out a logical argument based on only knowing where gamma-ray bursts were seen in the sky, not knowing anything about what they were, and based on just where they were seen in the sky, was able to convince people that they were actually beyond our galaxy, very far away at what's known as cosmological distances.
Right.
So, the basic premise of this argument is if there was something in the nearby universe, or in our galaxy, the distribution would be dependent on the structure of our galaxy. Okay. So can you show the structure of our? You have an image for the structure of our galaxy?
Oh, I
on
can show
there?
you the structure of the galaxy. I got it in my back pocket.
Okay.
It is awesome. Let me see here.
Okay.
Always come prepared with
Yep.
pretty pictures.
Yes,
All right, here we go.
that's helpful. Okay, so basically we live in a disk galaxy, and the galaxy has several important components. It's got a disk where a lot of the stars are, and it's got a galactic bulge in the center, which is sort of a cloud of sort of spherical-ish cloud of stars and gas and dust, and then it has a sort of halo, which is a sort of spherical-ish distribution where there are things like globular clusters, which are very, very ancient clusters, usually pretty ancient clusters of stars that are sort of surrounding the galaxy in a sort of spherical-ish distribution. And then, you know, we're somewhere in the disk. Our sun is somewhere in the disk. And
hello, I'm the sun.
yeah. And so if you see something, so depending on how you see things distributed in the sky, that can tell you about what part of the galaxy they might be in. So can you show the picture of the nearby stars?
Yep.
Distribution of nearby stars.
Mm-hmm. Let's see.
So this paper that I was saying that Bohdan Paczynski wrote has several distributions of things in the galaxy or outside the galaxy, just showing how they're laid out. So this is a picture of the nearby stars, and with the nearby stars, they're pretty isotropic, so sort of in the same, distributed the same in all directions, with just a little bit of clustering where they're you know, in binary systems or in little clusters, and those are things that are like less than 100 or less than a few hundred light years away, so really close by things.
Right.
And that's because very close to us in the disk of the galaxy, there's not a lot of structure. It's sort of uniform, very, very nearby. But then when you go out a little bit farther, can you show the one with the PN thing?
I'm reading your mind. That's cool.
Okay.
Although I'm not going to be doing this at your talks. If you yell next slide, I will give you a dirty look.
All right. So this is a distribution. These are actually planetary nebulae, which are it has nothing to do with planets, but these are like the remnants of supernovae. But these are things that are related to stuff that lives in the disk of the galaxy. And so this is a distribution. I should explain. This is like a plot of like the whole sky projected in this weird way. So the center is the center of the galaxy, and the distribution is sort of showing where on the sky everything is. And so you can tell from this picture that the stuff you're looking at is stuff that's in the disk of the galaxy, right? So that tells you that if you go a little bit farther out from our nearby stars, you start to pick up the structure of the disk of the galaxy. So these are things that are, you know, within a few thousand light years away. And then if you look at something that's a little bit farther away, you might pick up the bulge of the galaxy. Or the halo of the galaxy. So do you have the one with
the radio?
No, the globular clusters, GCs.
I do not.
Oh, okay. Something with
Here, let me just pull it through.
So okay. So if you go a little bit farther away, you start to see the structure of the center of the galaxy. Do you have?
Yeah, I didn't see anything with globular clusters.
Okay, that's all right. So you can pick up the distribution for the center of the galaxy, or if you go to a really distant, or if you look at nearby galaxies. So if you're just beyond our galaxy, and you're looking at nearby galaxies, then you start to see like the structure of galaxies being distributed along clusters and filaments. So this is a picture of how the nearby galaxies are laid out, and you see these sort of lines and groups of galaxies. And so that's when you're looking a little bit farther away, so you're still picking up like the structure of the local galaxies. And so the distribution tells you that whatever these things are, they're distributed like maybe a few million light years away.
Right.
But the gamma-ray bursts, the distribution of gamma-ray bursts is isotropic in a way that corresponds to being so far away that you're not anymore picking up the local galaxy distribution even. You're certainly not picking up the galaxy. For other reasons, we know that they can't be nearby stars, but they're distributed in this really uniform way such that they really have to be so far away that they just reflect the uniformity of the universe as a whole, more or less. So they don't have any structure in their distribution. And this image of the distribution of gamma rays gamma ray bursts, and the argument of how different objects are distributed in the universe was sort of the winning argument for why gamma ray bursts had to be at very large distances, because they have to be so far away that they don't have anything to do with our galaxy, or else they would be in some kind of shape that corresponds to our galaxy, and they don't have anything to do with the nearby galaxies in our local group, or else they would be in these sort of filamentary distributions. Right. And so this paper by Boda and Patinsky just lays that all out, shows all the distributions of these various objects.
And then mic drop, and he's done. Like, there you go.
Yeah, exactly. Yeah, it's a purely logical argument,
right,
just based on knowing nothing about what gamma ray bursts are, only knowing where they are seen in the sky. This was in 1995. We had very little information about what gamma ray bursts could have been made of. We had very little, of the tools we have now to study them. And he just totally solved that question just by saying, look, these are where we see them in the sky. They have to be really far away.
Use your brain. Come on.
Yeah.
And it's when you showed me this paper last week or earlier this week. It was really cool on how it broke it down. Like, this is awesome. It's not like you don't have to go and sift through a bunch of jargon to figure out what's going on. It's just like, well, because this is what we see, and if we look out this way, it looks like this and this and this. Well, since it doesn't match any of these things, then it needs to be out there, and I love it. It's such a clear, concise way of really profound science without needing to have a translation unit there to really get deep into it.
Yeah, and once we knew that gamma ray bursts were really far away, then we knew how energetic they were, and that helped us to figure out ideas for what could be causing them. So this was a really important piece of information to learn about how these things happen in the universe. And so then we learned a lot about how stars die and what the radiation that comes from those could look like. So really, really cool result. And the other cool thing about it is showing that isotropic, the uniform distribution, is a really nice illustration of the Copernican principle, which is this idea that the universe is basically homogeneous and isotropic. It's basically the same everywhere. We're not in a special part of the universe. Everywhere is basically the same.
Right.
And so
we're precious snowflakes, just like every other single precious snowflake.
Yeah, and there's no important direction or structure in the universe. We're kind of, every part of the universe is pretty similar to every other part, and so when you see something that's really far away, it's just showing that uniformity.
Right.
Of these gamma ray bursts too. So anyway, I'm a big fan of that paper and that result.
It sounds like what needs to happen is you and I need to make another video, like we did, because it's so well received. And I think we could totally dig into this a little bit more. But we have run out of time again. I don't know what it is. You and I just blow through a half hour, just like we're talking space and science and amazing ways for us to understand how the universe worked and how it's formed and where things are going on. We actually answered a lot of the questions that were coming in as we were talking. So I do want to thank those that were asking, like 72 from YouTube, Katie Stocco. I know Paul Stewart asked a question too. Aaron as well, my buddy Aaron. That he's watching us live and he wishes that he would have stayed in astronomy in college, but that's if you can't go back.
It's never too late to study.
Yeah, we're here, and there's so many awesome resources out there. I know MIT offers a bunch of free online courses for astronomy. I know Mike Brown, the Pluto Killer, is doing some free courses right now too. So there's a lot out there, and we'll be here on YouTube as well, and Twitter's.
Yes, we will.
And the Google Plus. And Facebook as well. And Friendster? Yes. Are you on Friendster?
No.
No, I never use Friends. We have a Tumblr, though. Space Fan News has a Tumblr. It's kind of creeping me out. I'm trying to use it. So, again, thank you, everybody, for watching. Katie, where can people find more about you and your awesome stuff?
Well, you can always find me on Twitter at AstroKatie. I'm on Twitter all the time. I haven't been tweeting that much lately because I've been a little bit under the weather, which you can probably hear in my voice. Sorry about that, but usually I'm on there talking science. I'm also on Facebook at facebook.com/AstroKatie, and I'm on Google Plus at +KatieMack. And you can find me on my webpage at astrokatie.com.
Oh, the Astro Katie! Woo! All right.
Yeah.
Again, I am Scott Lewis, and so actually, people in the future, because I will be linking this video in Space Fan News regular episode, which is coming out on Tuesday. So, hello, people from the future that are watching this. Stay cool. Don't do anything that Katie wouldn't do, because I would actually probably do a lot more than she would. Anyways, yeah, follow us on Space Fan News on Twitter. If you go to spacefannews.com, that is our Tumblr page. We're now over 2.2 million followers on Google+, so you guys are awesome. If you like this, if you want more, please subscribe, give us a thumbs up, and ask us more questions. A lot of the discussions that are coming up here are based off of your questions that you have for us. So if you have something you want to know or curious about the universe, let us know in the comments or tweet us or something like that, and we will most likely come up with an answer in video format for you. So thank you again all for watching, and as always, keep looking up.
Bye.